From predicting tomorrow's weather to designing brand new materials inside a supercomputer, simulations are, without a doubt, some of the most powerful tools we've ever invented. They let us see things that are totally invisible, test out the impossible, and basically build the future. But they all share one little secret.
That's it. Every single one. It doesn't matter how complicated it is or how much money was spent on it. No computer model can ever perfectly one-to-one capture reality. They are all, in some really fundamental way, flawed.
And that is the million-dollar question, isn't it? I mean, if we know they're all just approximations, how can we possibly use them to build bridges or design life-saving drugs or figure out how the universe works? Okay, let's really dive into this.
So, in fields like computational material science, simulations are absolutely essential. We're talking about modeling these incredibly complex processes, like how heat zips through a new metal alloy, or how a crystal structure bends and warps under massive stress. But here's the catch. The results you see on the screen, no matter how real they look, aren't guaranteed to be correct. They're actually a very, very carefully constructed illusion. Now, to pull back the curtain on this whole illusion, we're going to use a super simple analogy. Let's just forget about complex math for a minute and think about something we all use every single day, a digital map on your phone. This simple idea is going to unlock the 4 hidden flaws lurking inside every simulation. All right, let's play detective for a second. Using our map analogy, we're about to uncover the 4 fundamental sources of error that scientists and engineers have to wrestle with every single day. So the first, and let's be honest, the most obvious flaw in our map is that we're trying to put a 3D spherical Earth onto a 2D flat screen. It just doesn't fit perfectly. So right from the get-go, we have to make a choice, a simplification, just to get started. We're intentionally leaving out some of reality's complexity. This is what's known as modeling error, and it happens before anyone even writes a single line of code. It's when a scientist, for example, assumes a material behaves the same in all directions. The fancy word is isotropic. When in the real world, its properties might be totally different depending on which way you push on it. This isn't a mistake in the calculation. It's a flaw in the original blueprint. Okay, next problem. Picture a road that has this perfect, smooth curve in the real world. A computer can't actually draw a perfect curve. What it does instead is approximate it by drawing thousands of tiny, short, straight lines, all connected end to end. I mean, from a distance, it looks like a curve, but when you zoom in, it's really just a bunch of straight segments. In the world of simulation, this is called truncation error. You see, a lot of physical laws are described by these infinite mathematical series. To actually make them work on a computer, you have to cut, or truncate, that series off at some point. Just like with our road, we're swapping something infinite and perfect for something finite and practical, and that always introduces a tiny error. All right, next, let's zoom way in on just one point on our map. Now, a GPS coordinate could, in theory, have an infinite number of decimal places, right? But our computers, they have to chop it off somewhere. They just don't have unlimited memory to store every last digit forever and ever. And this little issue is called round-off error. It comes from the basic fact that computers store numbers with finite precision. A number like pi just has to get rounded. Now, one little rounding error doesn't seem like a big deal, but a simulation can involve millions or even billions of calculations. And these tiny, tiny errors can add up, they can compound on each other, and sometimes they can grow into a result that is just completely wrong. And for our last flaw, just look really closely at your map. A real city is a continuous landscape, right? It just exists. But on our screen, it's represented by a grid of separate, distinct points, pixels. We've taken a smooth, continuous reality and we've broken it down into a finite number of little, discrete pieces. This is a perfect picture of what's called discretization error. It's what happens when we take a real, continuous object, say a block of metal, and we virtually chop it up into a grid of tiny little blocks, or elements, for a computer to analyze. The accuracy of the entire simulation depends on just how fine that grid is. A coarse grid is faster, but a fine grid is way more accurate. So we've got these 4 hidden flaws, these little gremlins, baked into every single model. Now, knowing they exist is one thing, but how do scientists actually figure out if a simulation is reliable? How do they give it a health check? Well, it really comes down to 2 absolutely critical concepts, convergence and stability. Convergence is basically asking, If I make my model more detailed, if I make that grid finer or the time steps smaller, does my answer actually get closer to the true answer? And stability is asking, do all those little round-off errors we talked about stay small, or do they blow up like a snowball rolling downhill and just destroy the entire calculation? A healthy, trustworthy model has to do both.
Now, here's what's so cool about all this. Scientists don't just see these errors and throw their hands up. No way. They have a whole toolkit of strategies designed specifically to manage and control this chaos. They know they can't eliminate the errors entirely, but they can definitely tame them.
So how do they do it? Well, the whole process involves a few key steps. First, they can use something called mesh refinement. That's just a fancy way of saying they make the grid of pixels or elements much finer to cut down on that discretization error. They can use adaptive time steps, taking tiny little steps when things are changing fast and bigger ones when they're not, which helps maintain stability. They can use smarter, more accurate algorithms or higher order schemes to reduce those truncation errors. But the ultimate reality check, the final boss, that's validation, comparing the simulation's results to a real-world physical experiment.
Okay, I know this might all seem a little abstract, a little in the weeds, but understanding and controlling these errors has massive, and I mean massive, real-world consequences. This is not just an academic exercise.
Just think about it for a second. When you're simulating the 3D printing of a jet engine part, getting the heat transfer model right is literally the difference between a reliable component and catastrophic failure. When you're trying to predict how metal will behave under extreme stress in a building or a car, an unstable model could spit out a prediction that is disastrously wrong. This is where the digital world smacks right into the physical world, and accuracy is everything. And that really brings us to the most important point. The genius of modern simulation isn't about creating a perfect, error-free copy of reality. We know now that's impossible. The real genius lies in understanding, measuring, and managing all the imperfections to produce a result that is reliable and trustworthy enough to build our future on.
It really makes you think, doesn't it? We rely on these super complex digital models for everything, from financial markets to climate predictions. This little peek behind the curtain shows us that every single one of them is an approximation. So the next time you see a complex simulation, you can ask the right question. Not, is it perfect, but is it reliable?